Hello, everybody. Welcome back. Today we're going to be looking at Unit 8.2, which is on the pH and pOH of strong acids and bases. So get your calculators out, you're going to need them, and let's get started. All right, well, let's start off with a little bit of review of what the word strong even means in the first place. In terms of an acid, okay, really, or a base, the word strong means complete dissociation, complete ionization, okay? And just as an example, hydrochloric acid is an example of a strong acid. And if you look at this reaction, hydrochloric acid is doing what Bronsted-Lowry acids do. It's donating its hydrogen to the water. And the fact that it is a strong acid means that we're going to essentially, this reaction is essentially going to go to completion. Meaning at the end of the reaction, there will be very little, if any, HCl molecules. They are all going to be converted into hydronium and the chloride ion. Now, the nice thing is, when we're doing strong acid calculations, these are usually very quick calculations. And the reason is, remember, if you back to our previous lesson, that what you need to determine a pH is the molarity of H+. Guys, remember H+ is just a shorthand for H3O+. They mean the same thing. That is very easy to determine the pH of a strong acid because whatever the original molarity of the acid is, that's what I'm representing there with HA. Whatever that original molarity was, because that acid completely dissociates, the molarity will remain the same for the H+. And from there, it's very easy to calculate a pH. Now, if you will recall back to our solubility rules, we had a rule related to acids, and it listed these 6 acids. These are the 6 strong acids that you need to know. Commit them to memory, ladies and gentlemen. Okay, so these 6 are the acids that completely dissociate. One thing I do want to just highlight for you is that sulfuric acid here, each hydrogen comes off one at a time. It is only the first hydrogen coming off, being donated, that is a complete dissociation. The second hydrogen doesn't come off so easily. That makes it a weak acid. We'll talk more about that later. Okay. And I have a little memory trick here to help you commit these 6 strong acids to memory. All right, and the phrase is, imagine a perfectly clear, breezy summer night. I imagine hydroiodic. Perfectly, perchloric. Clear, hydrochloric. Breezy, hydrobromic. Sulfuric, summer, sulfuric. Night, nitric. It is absolutely imperative, ladies and gentlemen, that you commit these acids to memory. So these are the 6 strong. Any acid that is not in that list must be a weak acid, will not completely dissociate, and we're going to talk more about weak acids in a later lesson. So as we said, they completely dissociate. The math is usually very quick because the molarity of the acid as a whole is also going to be the molarity of the H+ because of that complete dissociation. In a strong acid solution, the molarity of OH- is going to be very, very small. Okay, and think about it. This is an equation we looked at in our last lesson. If this molarity is relatively high, it's a relatively large number, that means the OH- must be very, very small because of that relationship. Okay. And I'm going to come back and address that bullet in just a second. Okay, so let's just look at a very quick little calculation here. It says calculate the pH of a 0.2 molar solution of HCl. Immediately I recognize, okay, HCl, that is one of my 6 strong acids. And so, because that is the case, I can assume this, that the H plus concentration is also 0.20 molar. Again, because of that complete dissociation. Let's remember what the formula is to calculate pH. All right, if we take the negative log of 0.20, let's round it to 2 significant figures. That gives me this pH. Okay, and that should make sense to you. Okay, that's a very low pH, and it should be. This is a strong acid. Okay, strong acids typically have very low, very acidic pHs. Okay, look at this second one. Same question, different molarity and different acid. This is nitric acid, which is one of my 6 strong. Okay, now if you just kind of went into autopilot mode and you said, okay, there's the molarity of the acid, that's going to be the molarity of the H plus ion as well. Let me take the negative log of that number. Ladies and gentlemen, that's going to give you a pH of 9. And I want you to think about that number for a second. What kind of sense does that make? This is a strong acid. How could it possibly have a pH in the basic range? That doesn't make sense. And that's because that's not correct. Okay, look at this bullet now. When you're dealing this, and by the way, guys, this applies to strong acids only. If the molarity of your strong acid is so dilute, how dilute? Well, less than 10 to the negative 7th. That means that it is so dilute that water is in fact the dominant acid in that scenario. Okay? That means water is actually donating away more H plus ions than this very dilute strong acid. And guess what, guys? If water is your dominant acid, guess what the pH is? The pH is equal to 7.00. Okay. Does this situation come up frequently? No, it doesn't. Okay. But it comes up on occasion. And again, it applies to strong acids only. If the molarity of your strong acid is less than 10 to the negative 7th, it is so dilute that water is in fact the dominant acid, and you'll get a pH of 7. Okay, how about strong bases? Well, guess what? The word strong means the same thing. Okay, it's used in the same sense. It is meaning complete dissociation. The only difference here is we're not getting a hydronium or hydrogen ion on the product side. This time we're getting a hydroxide ion. I made you memorize your strong acids. Ladies and gentlemen, you need to memorize your strong bases as well. Okay? What do I mean by group 1 hydroxides? That means any metal, any group 1 alkali metal joined to hydroxide. Lithium hydroxide, sodium hydroxide, potassium hydroxide. Those are all strong bases. From group 2, you have 3 of them: calcium, barium, and strontium hydroxide. Okay? I always hear my students saying, okay, which ones are the strong bases? And I kept hearing them years ago saying cabasser. And I was like, What are they saying? Cabasser, calcium, barium, strontium. It was their funny little way of remembering those strong bases. Just don't forget it's also group 1 as well. So all of those bases completely ionize when they're in an aqueous solution. Okay, so let's just work one together, all right, and see how we do. Okay, it says calculate the concentration of an aqueous KOH solution that has a pH of 10.5. Well, right off the bat, I recognize, okay, this is one of my strong bases. Okay, so I'm going to write, in fact, you know what I'll do? I'm going to open up a new screen. Okay, so let's think about the formula for KOH and how that would completely dissociate. Okay, they told us the pH was 10.50. And that makes sense, it's a base. Okay, well let's turn that into a pOH. Okay, 14 minus 10.5. There's my pOH, and let's think, if this is what I'm trying to find the molarity of, let's think about what we could do next. How about if we use this equation? Okay, I'm going to plug in my pOH. And to invert a log, we do 10 to the power of negative 3.5. And I get this. I'm going to round my answer to 2 significant figures. Okay, now that's not quite the final answer. That is the molarity of OH minus. This problem actually asked us to find the molarity of the base as a whole. But ladies and gentlemen, do you recognize that these two things are in a 1-to-1 ratio? So guess what? It'll be the same number. Now, is that the case for all bases? No, it isn't. And we don't really have to deal with this with acids so much, but 3 of our strong bases come from group 2 hydroxides. So look at this problem. It says a 0.015 molar solution of strontium hydroxide has what pH? Okay, well, let's start off just like we did with the other one. Let's write out the equation for how this base is going to dissociate. There's 2 hydroxides in there. Okay, got to make sure you have a balanced equation. And let me come back here. What did they give us? They said that the solution, the molarity of SrOH2 is 0.015. Well, based on the stoichiometry, ladies and gentlemen, based on the fact that these are in a 1-to-2 ratio, hopefully you can recognize that the OH minus concentration is going to be double 0.015. It will be 0.030. And think about where you can go from there. Can't you now find the pOH and let's see what that gives us. Negative log of 0.030. Okay, so my pOH is 1.52. The problem wanted us to calculate the pH. So if I do 14 minus that pOH, Final answer. And I want you guys to start getting in the habit of asking yourself, does my answer make sense? You're going to get so sick of hearing me ask you that. Think about the situation here. We have a strong base. Does a pH of 12.48, does that make sense? Absolutely, it does. That pH is in the basic range, and it's kind of high in the basic range, and that makes sense for a strong base. So in general, guys, these strong acid and base calculations are usually pretty quick. So let's look at some practice AP kinds of questions. I'm going to work this one with you, and then I'm going to give you a chance to do some on your own. All right, this one says a solution is prepared by adding 50 milliliters of water to 50 milliliters of a 0.0001 molar solution of barium hydroxide at 25 degrees. Which of the following values is the best estimate of the pH of this new solution? And it's multiple choice. So let's imagine this is a real AP exam question where you do not have a calculator. Guys, it's a basic solution. I would hope that you would immediately be able to eliminate answer choices A and B because those are acidic pHs. Okay, those don't make sense. We could at least narrow it down between C and D, but let's talk it out. So what's going on here? I have a sample of a barium hydroxide solution. And what am I doing to it? I'm just diluting it, which, ladies and gentlemen, if you remember, this is the dilution equation. M1V1 equals M2V2. Okay, this barium hydroxide, before it was diluted, there's M1. This was before it was diluted. After it's diluted, I don't know what its molarity is. That's what we're going to find out, but it's total volume now because I added 50 milliliters of water. The total volume there is 100. Okay, so this is the molarity of my barium hydroxide solution, and I get this. Okay, now, remember guys, when you're finding a pH, you need to know the pOH, or you need to know the H plus concentration or the OH minus concentration to help you get you there. At the moment, this is not a hydroxide ion concentration. This is the concentration of the whole compound. Think about the balanced equation when this base dissociates. Oops. Okay, we just solved for the molarity of this guy. So what is going to be the molarity of OH minus? It's going to be double that number, which gives me this. All right. What would be the logical next step to find? Probably the pOH. Okay, now if you've been using a calculator as you've been doing this with me, put it down. Remember, we talked about estimating pHs and pOHs. To find this pOH, if I take the negative log of this hydroxide concentration, the pOH is going to be equal to exactly 4. And then from here it's easy. 14 minus 4, the pH is 10. So D is my answer. Okay, that is something the AP exam would expect you to be able to do without a calculator. All right. So here's another multiple choice question. This one is addressing sort of a different situation, but I want you to pause the video, see if you can solve this one on your own. Okay, so it says that we have 0.02 molar solutions of all these acids and bases, and we are supposed to rank them from lowest pH to highest pH. Let me say that to you in another way. Most acidic to most basic. Okay, so let's look at these 4 species that we're dealing with, and let's decide, you know, what are these things? Well, HCN is an acid. It is not one of my 6 strong, so this is a weak acid. HBr is one of the 6 strong, so I'm going to write strong. Okay, so before I go any further, based on the fact that HBr is strong and HCN is weak, an equal molar solution of those 2 acids, the strong acid should be more acidic. It's going to have a lower pH. So right away, I'm going to eliminate A and D because that weak acid is not going to be the most acidic. Okay, so now it's down between B and C. Now this is a little tricky because both of the bases here, both of the bases are strong. But come back up here. We have 0.02 molar of all of these solutions and both of these bases. But the strontium hydroxide, remember, it's got 2 hydroxide in there when it dissociates. It's going to have 0.04 molar for its OH minus concentration. Strontium hydroxide is going to have a higher molarity of hydroxide, and that's going to determine the pOH and thus the pH. So because strontium hydroxide is going to be providing double the amount of hydroxide ion, that's going to cause that solution to be the most basic. So B is my answer. Okay, so sometimes you'll have conceptual questions like that. Okay, so here's one more question. This kind of pulls a lot of the topics together. This is more like what you would see in a free response situation. So pause the video, see how you do with it. Okay, so let's look at the situation here. We've got an acid, HI, one of our strong ones. They give us a volume, they give us a molarity. We're given LiOH, one of our strong bases. We're given the volume, but we don't know the molarity. And part A says, what is the pH of the HI solution? Well, this one should be pretty quick. Hopefully you did this pretty easily. We're given the molarity of the acid itself, that strong acid. So if you look at what I've got for letter A, because it's strong, I know that the molarity of the acid itself is going to be equal to the molarity of H+, which I can then just substitute into my pH equals negative log of H+ equation, and I get a pH of 1.43. Ask yourself, does it make sense? It does. It's a strong acid. It should have a low pH. Okay, let's look at part B. It says the pH of the LiOH solution was found to be 8.250. Makes sense, it's basic. What is the molarity of the LiOH? This is basically just going backwards. So for letter B, we're told the pH. The first thing I did was I said, okay, well then what's the pOH? 14 minus 8.25, and I get my pOH, which I then substituted into pOH equals negative log of the hydroxide concentration, and I was able to solve for the hydroxide ion concentration. And because lithium hydroxide releases just one hydroxide ion. They're in a 1-to-1 ratio. These two molarities are equal to one another. That would not be the case if this base was like calcium hydroxide, but since it's a base that only contains one hydroxide ion, they are in fact equal. Last part, we're going to take these two solutions and we're going to pour them together. And it says, what is the molarity of the lithium ion when these solutions are combined? Okay, well, in the previous part, letter B, we just found the molarity for LiOH. I know that the molarity of Li plus, before we pour that other solution in there, is going to be the same. They're in a 1-to-1 ratio. Okay, so it ends up being, that's the same number. Now that's before the dilution, before we added that acid. Because we're going to add another solution, I'm going to use that dilution equation. I've used the left side, M1 and V1, as sort of like before the dilution, and the right-hand side as after. Plug it in, solve for that new molarity, and that's what we get. Okay, so that's an example of, what a, free response situation could look like. So that's it for 8.2. Hopefully you didn't find that too taxing. It wasn't too bad. And I hope you have learned a little something today, and I look forward to seeing you next time.